Guys, welcome back to Techdose, and in this video we will see distribute candies among children 2 problem, which is based on Leetcode number 2929. It is based on combinatorics along with the set theory. Now let's read the problem statement. You are given two positive integers n and limit. We need to return the total number of ways to distribute n candies among 3 children such that no child gets more than limit number of candies. Okay. Now if you look at this first example, you have a total of 5 candies and the limit is 2. That means no child can get more than limit number of candies, and if you try to distribute them among 3 different children, then you can do it in 1 2 2, as the child 1 gets 1 candy, child 2 gets 2 candy, and child 3 gets 2 candy. You can also do it as 2 1 2 or 2 2 1. So there are only 3 ways, and that is why the answer is 3. In this case, the total n value, that means total number of candies, can go to 10 to the power of 6, and the limit can also go to 10 to the power of 6. Now we need to write an algorithm in such a way that we take less than 10 to the power 8 computations overall, so that we pass it within 1 second, right? So let's see how we can solve this problem. Before we start discussing the problem, we need to understand a theorem which is stars and bars. It is a very popular theorem in combinatorics. It says that the number of ways to put n identical objects into k labeled boxes is given as n plus 2 c2. Okay. Now how is this coming? Let's say that you have n number of stars. You have n stars and you want to put all the n stars in 3 boxes. Let's say you want to put it under 3 boxes. Then for dividing n stars into 3 divisions, we will be taking 2 number of bars. Okay, because to the left side of this bar 1 we will consider box 1, in between bar 1 and bar 2 we will be considering box 2, and to the right hand side of bar 2 we will be considering box 3. So if you look at this arrangement, it will always be possible to divide the number of stars into k number of boxes if you take k minus 1 number of bars. With 2 bars you can represent 3 boxes, with 3 bars you can represent 4 boxes. If you put bar 3 in between, you will see box 1, box 2, box 3, box 4, right? So that will be the arrangement. Now let's talk about this case, because in our problem statement it is asking about distributing n number of candies among 3 children. So that's why I want to talk about 3 groupings. So in order to group all the candies, that means all the stars, into 3 divisions, we need 2 dividers, you can say, right? 2 dividers or 2 bars. Now in how many ways can you arrange these bars? Well, how many positions are there? So n number of items which are the stars or the candies, and then 2 extra items for the bars. Okay, so total positions are n plus 2. Out of these total positions, we need to pick 2 positions, right? So in how many ways can you pick 2 items out of n plus 2 items? You can do that in n plus 2 c2 ways, right? And that is why the number of ways to arrange the stars and bars to get the stars into the boxes will be n plus 2 c2. That is the reason, because we are just selecting the position of bar 1 and bar 2 from the total available n plus 2 positions. We have to pick only 2 positions where we can place bar 1 and bar 2. And that is why the count will be n plus 2 c2. Now let's say that if I generalize the solution for k number of boxes, we need k minus 1 number of bars, and so the total positions will be n plus k minus 1. Okay, the number of candies plus the number of bars, number of stars plus number of bars. And within this you want to select k minus 1 positions to place k minus 1 bars, and that is why the formulation will be n plus k minus 1 c k minus 1. Right? In this case we are solving for k equals to 3, because we want to make 3 groupings. Okay. Now you can also see that the bar can also be present right in the beginning, and if the bar 1 is present right in the beginning, then in that case the first box will be empty. It will be having 0 number of stars. Also the bar 2 can be placed at the right hand side, and in such case the box 3 will be empty, or the 2 bars can be placed together. So in that case the box 1 and box 2 can get empty. So you can do multiple type of arrangements in such a way that you can say that the box item count will be greater than equals to 0. That means any of the boxes count can also be made as 0, because if you just want to make, let's say, box 2 0 but not box 1 and box 3, then you can bring this bar 2 adjacent to bar 1, and in that case box 1 and box 3 will not be empty, but box 2 here will be empty. So any of the boxes can be empty, and that is why we can make the statement that box item count will always be greater than equals to 0, because they can be 0 as well. So when I write this formulation n plus 2 C2, then this means that we are counting the total number of ways in our candy problem. We are counting the total number of ways in which we can distribute n candies among k number of children. N candies among k number of children. In our case, if you write n plus 2 C2, then we are trying to distribute n candies among 3 children. So there is no limit to how many candies a child can get. In the problem statement, it was mentioning about a limit, isn't it? So if I ignore this limit, then you will get the total count to be n plus 2 C2. Okay, where each of the child can get candy count greater than equals to 0, and if it is greater than equals to 0, then it will also by default count everything which is also greater than limit, isn't it? So I hope this is clear how this n plus 2 C2 has come. Now let's think about our goal and match up with the previous case of stars and bars. Our goal of the problem is to count the number of ways to distribute n candies among 3 children so that nobody gets more than the limit candies. And what does this formulation represent, n plus 2 C2? It is representing the number of ways to distribute n candies among 3 children, where anyone can get any number of candies. Okay, so it is having all the valid counts plus all the invalid counts. The valid counts are the ones where none of the child gets candy count greater than limit, and the invalid count indicates that at least one of the child gets the candy count greater than the limit, isn't it? So if I take all possible combinations, all possible distribution combination, and say that it is the universal set U, from there if I subtract all the invalid combinations, then it will be giving me the valid combinations, because you know what, the valid combinations plus invalid combinations forms the universal set U. That means all possible combinations. So if you just rearrange it, then you will get all the valid combinations will be universal count. That means the total count minus the invalid combinations, right? That is what we will try to do here. So I have to now determine how to get the count where one child gets candies greater than limit, exactly 2 children gets candies greater than the limit, and exactly 3 children gets the candies greater than limit. So for counting this, actually our set theory will help us in solving this problem, because there is a proper concept of using Venn diagram and calculating all these values. Now let's use the set theory logic in order to actually get the valid combination count. So in this case, let me explain this Venn diagram. The universal set, as I explained, will be representing all possible combination, valid plus invalid. So we already know that all possible combination, that means the number of ways to distribute n number of candies to 3 number of child will be equals to n plus 2 C2. You already know that. Now let's say the first child gets x1 number of candies, second child gets x2 number of candies, third child gets x3 number of candies. Then the total candies must always add up to be n, which is the total number of candies. Okay, and each of the candy count, that means each child can get the candy count greater than equals to 0, right? Now if you look at this diagram, let me explain you what is the meaning of this A1. The meaning of this A1 here, which is this one, right? The meaning of A1 representing is when the first child gets the candy count greater than the limit. That is the meaning of this A1. The meaning of this A2 here means only this part, okay? The A2 means when the second child gets the candy count greater than limit. The meaning of this A3 here means that when the third child gets the candy count greater than limit, right? Now what is the meaning of this A12? meaning of A12 is when the first child and the second child both gets the candy count greater than limit. Similarly, A13 means when both the first child and the third child gets the candy count greater than limit. And 23, A23 means that when the second child and the third child gets the candy count greater than limit. When I say about A12, then only the first child and second child gets the candy count greater than limit, but the third child do not. Now similarly, the meaning of this A1, 2, 3 will mean that first, second and third child, all of them gets the candy count greater than limit. Okay, so if you look at the problem statement says that we need to distribute n candies among 3 children such that no child gets more than the limit candies. And what is this representing? This boundary, inside this boundary, if you go inside this boundary, it will represent all the combinations where at least one child gets the candy count greater than the limit. Okay, and what is this boundary even representing? If you go through this boundary, it is representing A1 union A2 union A3. That is what it is representing, right? So this universal set is representing all valid combination, which is n plus 2c2, and this boundary, that means all the invalid combinations here, are being represented by A1 union A2 union A3. So if I take this n plus 2c2 and I subtract this value A1 union A2 union A3, then I will get all valid combination, and this will be all valid combinations. You see, this outside portion, which is outside of all the 3 circles, will be representing all the valid combinations where you can distribute n candies to all the 3 children so that none of them get candy count greater than limit. Okay, so that is my goal. My goal is to get the universal set minus A1 union A2 union A3. So I know about the universal set because I know about the n value. So this can be easily calculated in order of 1 time. Okay, because what is n plus 2c2? N plus 2c2 will be simply, you can say, n plus 2 factorial divided by n plus 2 minus 2 factorial into 2 factorial. That is what is the meaning of n plus 2c2, and this can be represented as n plus 2 times n plus 1 divided by 2. Okay, so this multiplication is a simple multiplication and you can get it very easily, isn't it? So that is an O1 calculation. So my main problem is to calculate A1 union A2 union A3. That is the entire crux of this problem. So let's try to understand step by step. Now let's say that I know already that in whatever way I distribute the candies between the first child, second child and third child, the total count has to be n. I am assuming that one of the child, at least one of the child will be getting a candy count greater than the limit value. Okay, and let's call it AI. At least one of them gets the candy count greater than the limit value. Okay, so in this case, let that child be A1 who gets the candy count greater than the limit value. So if A1 gets the candy count greater than the limit value, then you know that x1 here will be greater than the limit value. So what is the minimum value of x1? The minimum value of x1 will be limit plus 1. Okay, because it has to be greater than limit. So I'm taking integer calculations. So in this case, if I have to represent in the format where all the xi's are greater than equals to 0, then I have to subtract this limit plus 1 on both the side so that I get x1 minus limit plus 1 equals to 0. So in this case, I can say that this entire value is greater than equals to 0, and that is what I'm trying to do here. X1 minus limit plus 1. Now what is the use of doing this? When I know x1 is greater than limit, then what is the use of doing this? The use of it is, if I can represent it by a separate variable, let's say y1, then in that case I can say that y1 plus x2 plus x3 is equals to this given value. Why this given value? Because I am subtracting with this value on both the side to maintain the equality. Otherwise you cannot maintain the equality. Okay, so taking x1, I am subtracting limit plus 1 on both the side. So on the left side I am assuming this term to be y1. On the right hand side you have n minus limit plus 1. So if you can represent it in this way, then you know that if you have to count all possible distribution of this y1 plus x2 plus x3, then you can use the same formulation n plus 2 c2. That is why I am doing all these things. Okay, so y1, x2, x3 are all greater than equals to 0, and you know it is equals to this value. So you can say that the total number of ways to do this distribution, that means this is the count, this is the total count. Okay, so the total number of ways to do this distribution will be this total count c2. That's the only thing that you have to do, right? And you know how to calculate this. You just take this value and multiply it by the +1 factor of this and divide by 2, as I had already shown you here, right? Something like this. So this n term can be replaced by this particular term. Okay, so that is why I am doing this conversion. Okay, therefore the number of ways to get this distribution will be n minus limit plus 1 c2. Okay, I hope this is clear. Now in this case I assumed that the first child actually gets the candy count greater than the limit, but it can also happen to the second child or the third child as well. Therefore the same count will occur, exact same count will happen whatever child you assume. So I will be taking this term and multiplying this by 3 because I will get the same count, isn't it? So this is giving me the total ways to get at least one child candy count greater than limit. At least one. It is not exactly one. Okay, so it is also covering the case of 2 and 3 times. Now if you look at what we actually did for this a1 here, what did we calculate? So when we calculate this value for a1, then it is calculating this entire circle, not just this part. Okay, it is calculating the entire circle. Within this circle we have a1 plus a12 plus a123 plus a13. All these will be counted with this formulation. And again, if you repeat for this a2, then you will see it will contain a2 along with this a12 and a123 and a23. Similarly, when you do for a3, it will be combining a13, a123 and a23. So you will see that regions are getting double counted, and so those regions must be subtracted. So now how to subtract? We need to calculate this a12, a13, a23 and a123 as well, so that we can subtract the double counting, isn't it? So this is what we do for the entire circle calculation. Now once you have done that, similarly you can repeat for at least 2 children getting the candy count greater than limit. How to do that? Again, we will assume aij representing ai intersection aj, and in this case I know that if I assume x1, x2, x3 as the total number of candies being given to first child, second child, third child, total will be equals to n. Then in this case at least 2 children, ith and jth child, must get the candy count greater than limit. And according to the previous calculation, you can simply choose 2 children to be, let's say, a1 and a2, okay, the first child and the second child, and simply subtract the given value according to how I showed you the calculation, represent by y1, y2, and the third child will be unaffected because he will get the candy count less than equals to limit. Okay, and when you do this subtraction has to be also performed on the right hand side, and we are doing the same subtraction 2 times, so it is 2 times of limit plus 1. So this is the equation that you get, and you know how to calculate this equation because we already know how to calculate when x1, x2, x3 equals to n. All these calculations we know, right? So when we get this value, then you just have to apply c2 to it to get the total number of combinations. When you choose one pair, how many pairs are possible? You can either choose x1, x2, that means x1, x2 means what? a1, a2, both of them to get candy count greater than the limit, or a1, a3 to get the candy count greater than limit, or a2, a3 to get the candy count greater than limit, right? So there are 3 pairs. If you look at the diagram, there are 3 pairs, a12, a13 and a23. So again the multiplication factor 3 will be present to the one combination count because we have 3 possible combinations. So I think this is clear. Now we have to calculate a1, 2, 3 where all of them are exceeding the limit, and in that case for a1, 2, 3 we call it as a1 intersection a2 intersection a3, where I will say x1 plus x2 plus x3 equals n, and x1, x2, x3 all of them should be greater than limit. So in this case again I will repeat the same calculation, and I will subtract 3 times limit plus 1 because it has been subtracted 3 times on the left hand side, and you get this equation. And again, if you want to count the total combinations where all of them are exceeding the limit, you just apply C2 to it and you will get the total count. Now in this case all the 3 will only be possible in one way, because there is only one triplet with the 3 children, which is x1, x2, x3, right? So there is only one way, therefore 1 will be multiplied here, and that is why I am not multiplying anything. Fine. So now we have got all the count. We have got this total count for all the circles. We have got the count. Then we have got A12, A13, A23 and A123. So we can simply apply the inclusion exclusion principle of the set theory to get the valid combinations. In this case, how to calculate A1 union A2 union A3? A1 plus A2 plus A3 subtracted with A1 intersection A2 subtracted with A1 intersection A3 and A2 intersection A3, and you have to add A1 intersection A2 intersection A3. So there is a proof for this. You can always go ahead and read the proof how this is coming. This is out of scope in this video. Now we already know the values. A1 is meaning that at least one child, where the child is the first child, at least the first child gets the candy count greater than limit. A2 means at least the second child gets the candy count greater than limit. A3 means at least the third child gets the candy count greater than limit, and this was calculated here. Okay, now A1 intersection A2 is the A12 part. This we had calculated, and we also know that it will be repeating the same count for A13 and A23. So that is why we are multiplying this factor by 3, and this was also calculated previously. Now we can just take this formulation and say that this part is P, this part is Q, and the last part is R. So P minus Q plus R will give you A1 union A2 union A3, which is all the invalid combinations. And you know that universal set U will give you all the valid combination, which was n plus 2C2. So if you subtract from this value, which is the universal set, if you subtract this P minus Q plus R, then you will get all the valid combinations, because valid plus invalid combination will be equals to all combination, right? So that is why I will be doing this, and I hope you have understood how we are trying to calculate it. So in this case, all the calculations are O1 calculation. Therefore, the time complexity is O1 and space complexity is also O1. I hope it is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the n value and the limit value. So I'll be first calculating all combinations. So in the combinations, I will be sending an n value, and you know how to calculate n plus 2C2. We just need to take n plus 1 and multiply it by n plus 2 and divide it by 2. That is what I am doing here, and multiply it by 1 LL, which will convert this integer to a long integer. Okay, and I will repeat the process by just changing the values. These all values I had already explained you, and these values were already explained because they are repeating 3 times, and the last one is A1 intersection A2 intersection A3, which will only happen one time because there is only one triplet. The pairs were 3 in count. Triplet is only 1 in count. So this will give you 1 above limit combination, 2 above limit, and 3 above limit. And you know how to calculate this. This is A1 union A2 union A3, all the invalid combination, which is P minus Q plus R. That is what it is calculating. You take this value and subtract from the universal set minus P minus Q plus R, and that is how you will get all the valid combination, and we return it. So I hope this problem is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.